This is our first lesson for Math 171. So this is Module 1, Lesson 1. We're going to talk about how to interpret graphs. So what I would like for you to do is you go through each of these lessons each week. You'll want to print out the guided notes that will be provided for you in Blackboard. I have a copy of the printed notes here. And then you'll want to fill those out as we go through the material. So as you listen to the lesson. So just as though you were sitting in a face-to-face class, you'd have your notes. And then you would fill those out as we discuss the material in class. So the video is obviously set up so you can pause, you can return, you can review material. And so take that as you will. You know, you can speed it up if you need to, you can slow things down if you need to. There will be times throughout the video where I'll actually ask you to pause and go work a problem on your own, and then come back and listen to the explanation, or maybe fast forward to see the answer. So as we're going through this, I try to treat this very much the same as I would as if we were in a face-to-face class together. So there will be times when you'll just be listening to lecture and you'll be filling in the notes. There will be times when I'm asking you to go work a problem, come back and check the answer, similar to how you would if we were sitting in a classroom. So let's get started. So we're going to talk about interpreting graphs here. So we're going to start with some definitions. So the first definition we have is we know that the domain of a function, so that's our first blank here, the domain of a function is the set of all the inputs for the function. Okay, and so when we talk about domain, we're talking about x values. What sort of x values can I put into a function? Now I should talk about, when I talk about a function, I'm talking about something that's written in the format of f of x, maybe f of x equals x plus 2. And so that's, if that's my function, so function notation is the f of x, then I know that the domain are the inputs, or whatever the x values in are. So whatever that's the domain. And so if I have an input of maybe x is equal to 3, then I'd be looking at f of 3. And then this function tells me that I take whatever the x value is and I add 2 to it. So f of 3 would equal 3 plus 2, and then of course that equals 5. So this function, the function is just a rule. It tells me what to do. In this case, I take an x value and I add 2 to it, and that gives me the output, okay? So that's the next part of my definition. So the range of a function is the set of all the outputs associated with the inputs in the domain. So for all of those inputs, those x values, I'll have outputs. So those, of course, are my y values. Okay, so for my example here, my input for x was 3, my output for y was 5. And so that would give me the point for this function of, whoops, and then I wrote 2, of 3 is my x, 5 is my y value, so my input and my output. So we've got some examples, and we're asked to determine the domain and range of each of the functions, and we're going to write our answer in inequality notation and also in interval notation. Now, when we talk about inequality notation means we're going to use less than or equal to, greater than or equal to symbols. So those are inequalities. Interval notation means we're going to use brackets, okay, around our x and y values. So this may be x and y. Oops, not y. x1. We'll call this x1 to x2, and then we could use parentheses. We'll talk about the difference between these in just a second. Maybe between x1 and x2. Okay, so first we've got our graph here to the left. It's a graph of a polynomial. I know that because it's a smooth continuous curve, so that tells me it's a polynomial. And I'm looking at the domain. Now remember, domain are the x values. I want to know what sort of x values can I input into this function that produce a y value that's on the graph. Okay, if there are certain x values that don't give me y values, then they're not a part of the domain. So domain are x values that will produce a y value that exists on the graph. Okay, so when I read this graph, you read a book from left to right. Similarly, you read a graph from left to right. So I start with the left side of the graph, and I'm looking for what's the smallest x value that I can input to that will create a y value on the graph. So I can see that my graph starts here, and then as I move from left to right, so I can go across, and then my graph ends about here. Okay, so in terms of my x value. So the smallest x value that produces a point on this graph is -5. Okay. And because we're using inequality notation, I know my x values, my x will be greater than or equal to -5 up to 2. My largest x value is 2. Now notice there's an open circle at 2, which means that that point is actually not included on the graph. So all points up to 2, but not including 2, are included. So 1.9 is included, 1.99, 1.999, 1.9999. I could do this all day. Every x value up to, but not including 2, is on the graph. So from an inequality notation, x is going to be less than 2, not less than or equal to, because we don't want to include 2. Okay, now I'm ready to look at the y values on the graph. Well, for my y values, I can see my smallest y value is down here at -7. And then if I trace up the graph here, I can see that y values stop at a high of 3.38. Okay, so in inequality notation, I'm looking at my y values. I know that y is going to be greater than or equal to -7, less than or equal to, I should include less than or equal to 3.38. And so those are my y values. That's the range of the graph, okay? So x values are the domain, y values are the range. So you write your numbers just like on a number line. Smallest number is to the left, largest number is to the right, as we work from left to right. So x values are greater than or equal to -5, less than 2, and my y values are greater than or equal to -7, less than or equal to 3.38. So this should be a review. You've seen this, I'm sure, previously. Now, that's inequality notation. Now, if I asked you to write this in interval notation, okay, we're going to talk about whether or not you use a bracket, whether or not you use a parenthesis. So we use brackets, means the value is included, and a parenthesis means the value is excluded. Okay, so that's really the only difference. So we're going to convert what we've done in inequality notation above, and we're going to convert that. So from inequality notation, we're going to rewrite the same information in interval notation. Okay, so my domain then, I know that x is greater than or equal to -5. So it includes -5. So I'm going to use a bracket from -5 to my largest x value is 2. But 2 was excluded, 2 because x is less than 2 as opposed to less than or equal to 2, and so I'll use a parenthesis. For the range is greater than or equal to -7, and that is included, so I'm going to use a bracket, up to a value of 3.38, and again, 3.38 is included, so I'll use a bracket. Okay, so again, x values are my domain, and y values are my range. Now, we are going to use interval notation for everything we do this semester. So inequality notation is sort of nice for introducing this because it's a little bit easier for you guys to get your heads around, but we're going to use interval notation for everything going forward. You will not use inequality notation anywhere on your homework, your notes, your test, nothing. Okay, so we're done with inequality notation. There it was. Okay, now while we're here looking at this graph, let's go through a couple of other items. What if I asked you to find the x-intercept for this particular graph? What if I asked you to find the y-intercept for this particular graph? Now the x-intercept is where it crosses or touches the x-axis. So if you look at the graph, I actually have two x-intercepts. There's one here. And there's one here. Now remember that open circle, the graph doesn't exist there, so I don't include that. So my x-intercepts actually occur at -4, 0 and at 0, 0. Okay. Now notice something here. This notation is very, very similar. Okay. Interval notation could be written with two parentheses if you had 2 points where it didn't exist. Okay. Coordinate points, as in the x-intercept, is written with parentheses. They mean two entirely different things. And I think that's why math can be so confusing for students. We have a lot of notation that looks exactly the same, but means entirely two different things, okay? So you really need to pay careful attention to your notation. Be very careful how you write things. Be very careful how you make those differences, understand the differences between them. So for my x-intercepts, these are points, these are coordinate points. -4, 0 represents an x, y coordinate, okay? Whereas in the domain, when I have my domain value here, of -5, 2, those are both x values. My smallest x value was -5, my largest x value was 2, okay? And for the range, when I look at -7, 3.38, those are both y values. My smallest y value is -7, my largest value is 3.38, okay? So they mean entirely different things. So sometimes that can be confusing for students. All right, so back to where we were, let's look at the y-intercept. Now the y-intercept, remember, is where it touches or crosses the y-axis. So if I'm looking for the y-intercept, there's a y-intercept at 0, 0. Okay, so I have the point at 0, 0 is not only an x-intercept, it's also a y-intercept. Okay, so moving down below, we're going to determine the domain and range of the graph below. This is a graph of an absolute value function, okay? And so what I'd like you to do is I'd like you to pause the video, answer the questions, and while you're there, let's go ahead and just get some additional practice in. Go ahead and find the x-intercept and find the y-intercept as well. So after you get your answers, come back. You can fast forward the video a little bit, see if your answers are correct. If they are, move on. You don't need to listen to the explanation. If your answers are not correct or you're a little bit concerned or confused, then listen and I'll explain how it works. Okay, so the domain for this one, you should have gotten -infinity to infinity, because the graph, if it continues, you can assume these are arrows on the end, that it continues forever. And again, domain are x values. So my smallest x value, this goes all the way to -infinity. And if I continue to read from left to right, it will go all the way to positive infinity for x values. There are no breaks in the graph. For the range, now the range, I can see that the smallest value for y values, remember range is right from bottom to top. So the smallest value is 0, and then it goes all the way up to positive infinity. So the range will be from 0 with a bracket because it's included to infinity with a parenthesis. Now, side note, infinity always is with parentheses because it's not bounded. Okay, remember a bracket means I'm including a particular number. Well, you can't include the end of infinity. It's not possible. Whatever huge gargantuous number you give me and call infinity, I can add 1 to it and it's larger. So infinity will always be with parentheses, so make yourself a note there. The x-intercept here, again, is where it touches or crosses the x-axis. For this particular case, the x-intercept here is at 0, 0. And the y-intercept is where it touches or crosses the y-axis, also 0, 0. Whoops, this is the same point, obviously. Okay, these are the same x, y coordinates. They just mean two different things. So same x, y coordinates. Okay, it's just the same point on the graph that happens to be where it touches or crosses the. Okay, some more definitions. So we've already touched on this briefly before. So a function, that's your first blank. So a function f is a relation between two sets. Okay, so I have two sets of numbers. I have a set of numbers in the domain, or the x values. I have a set of number in the y values. And it's a relationship between those two sets of numbers. So a function is just a rule. Okay, so a function sounds like it's something really fancy, and it's really not. It's just a rule. It's a rule that assigns each element in the first set exactly one element in the second set. Okay, and the first set is what we call the domain of the function, and the second set is called the range of the function. And remember, domain are x values, range are y values. Okay, the independent variable is the variable associated with the domain, and then the dependent variable belongs to the range. Okay, so when we talk about independent and dependent variables, sometimes an easy way to remember this, dependent variable is always the y values, independent is the x values. So let's just create a scenario here that'll help. So let's create a graph. Maybe I have a graph that looks, I don't know, something like this. Okay. And let's say my x values represent the number of calories that I eat in a day, and the y values represent my weight. Now, obviously, as the number of calories increases, okay, as I move across, then my weight will also continue to increase. Now, in this scenario, the number of calories represents, of course, the x values, okay? And this is my independent variable. Okay. And then of course my weight are the y values, and that's my dependent variable. Now this is dependent because of this. My weight depends on how many calories I consume. Okay, so the number of calories I consume is independent. It doesn't depend on, it's, I don't know, it's independent. It's not affected by anything. That's a better way to say. So, you know, maybe in one day I eat 2,000 calories, maybe the next day I eat 1,400. I don't know, I'm all over the board. But my weight depends. So if I really, you know, ratchet up the number of calories that I'm consuming in the course of the week, maybe I'm training for something or I'm bodybuilding or whatever, then my weight will increase. My weight depends on how many calories I eat in the course of the day. So that kind of explains the difference between the independent and the dependent variable. Okay, so in our example below, we're supposed to determine whether the relation represents y as a function of x. Now, one thing to point out here in our definition is we said that a function is a rule that assigns to each element in the first set exactly one element in the second set. So we want to write that a little differently. What that means is that every x value has only one y value associated with it. Okay, so every element that's in the first set is the domain, has exactly one element in the second set, which means it has exactly one element in the range or one y value. Okay, and so if that's the case, if we have every x value has only one y value, then we know that these three little dots are red. Therefore, y is a function of x. Okay, and so if we look at our graph over here, we can go through and we can look at all of the x values. So let's just go through and choose a couple. So if I look at maybe -1, x is -1, then y is 1. If I look at -2, then I can see that y is 4. Maybe x is equal to 1/2. It tells me y is 1/4. Okay, and I can go through and I can do this for every x value. Okay, as I move along the x-axis, for every x value, I can see that there's only one associated y. And so what that tells me is that this is indeed a function, okay? Now, let's come up with a counterexample here. So sometimes it's easier to understand if you understand what it doesn't look like, okay? So maybe I have a graph that looks something like this. So a sideways parabola here. Let's create some values here. We'll call this, let's see, this value will be 3. This can be -3. We'll create a point here at 2. Okay, now I can see if I choose some values on this graph, the easy ones to find are, I have a point, I'm intending to have a point here at 0, 3, and 0, -3. Okay, so I have the point 0, 3 on the graph, 0, -3 on the graph. Well, now, if I'm looking at my x values, okay, if x is 0, then I can see that y can be 3 or y can be -3. So based on our definition where we said that every x value has only one y value associated with it, well, here I've got a scenario where if x is 0, y is 3, y is -3, okay? That fails this test. And so what that tells me is that for this particular graph, this is not a function. Okay, and I could look at other points on the graph here. Maybe I have a point over here at, I don't know, maybe that's, let's use a different color. Maybe this is -3, and then whatever this point is and this point are. My graph's not perfect. So 2, and maybe this is -2. Okay, and so in this scenario, I'd have to point 3, 2 on the graph and 3, -2 on the graph. And so, sorry, -3, 2, -3, -2. Let me write that. -3, 2, -3, -2. And so again, my x value is -3, but it maps to two different y values. So again, this is not a function. Now, This is easy enough to understand, and you can review these graphs and go through and look at all the x values and determine whether or not there's more than one y value associated with it. But that can be a little tedious, especially if you have a very complicated graph. And so let's go with an easier definition, because easier makes life better. Okay, and so what we're going to use is we're going to use the vertical line test. The vertical line test says this: a graph represents a function only if every vertical line, that's your blank, intersects the graph at most once. Okay, and if that's true, then we know that this graph is a function. So a graph that fails this test does not represent a function. Okay, and if you want to look up above, you can see, if we were to use the vertical line test above, if I were to draw vertical lines through this graph, I intersect the graph at only one place. It doesn't matter where I draw my vertical line, I intersect in only one place. But in our counter example over here, if I draw a line, you can see I intersect the graph in more than one place. Okay, so here I intersect twice, here I intersect twice, and so I can see that that fails the vertical line test, and so it's not a function. So much easier to deal with. It's much quicker to be able to look at the vertical line test, or just, visualize and be able to tell me whether or not it's a function or not. So that's what we're going to use. Okay, so in our examples below, we're going to use the vertical line test to determine whether each of the following graphs represents y as a function of x. So what I'd like for you to do is I'd like you to pause the video, answer each one of these, and then come back and check your work. Okay, so for the first one, you should have that, yes, this is a function. Okay, because you can see anywhere that you input a vertical line, you're not going to intersect in more than one place. For the second one, yes, this is also a function. Now this one's a little trickier, okay, because I can see that if I use my vertical line test, I'm fine in all these areas, but I need to understand here where the 2 points overlap. So if I come through, okay, I intersect the graph once there, but then I go through again here. But the fact that this is an open circle is the key. The open circle means the graph does not exist there. So at this particular point, I'm still only intersecting the graph in one point, which means, yes, this is a function. Now, if that had not been an open circle, if instead, let's see if I can change this, if instead, let's assume that this had been a closed circle, okay, then when I drew my vertical line through, I would have actually intersected the graph in 2 points, the point on top in black and the point in green below, and that would have failed the test, and that would have not been a function. It only has to fail in one place on the graph in order for it not to be a function. Okay, so if that had just been a closed circle, this would not have been a function. Okay, and then finally, my third, I can see it, all kinds of places that I failed the vertical line test. So no, this is not a function. So now we're ready to practice reading a graph. So you've got the graph here of a polynomial function. Again, a polynomial is just a smooth, continuous curve, okay? And then I've got a list of questions here for you, A through G, or a number of questions. And then down below, what is the domain of f of x in interval notation? I want you to answer that one as well. And then also below that, what's the range of f of x in interval notation? So we're going to talk through a couple of things here first, and then I'm going to turn you loose to take a shot of this on your own. So first off, you can see in part A, I'm asking you to evaluate f of 0. So again, as a reminder, when I look at a function, it's f of x is equal to y. So if I'm asking you to evaluate 0, then I want to know when x is equal to 0, what's the value for y? That's what I'm asking you to determine. If you look at part D, you can identify the x and the y intercepts. Remember, the x-intercept, just as a refresher, is where it touches or crosses the x-axis. And then similarly, the y-intercept is where it touches or crosses the y-axis. Okay, you're going to write these as coordinate points. So coordinate points are x, y coordinates. Okay, and then for the two questions below, what's the domain and what is the range of f of x in interval notation? So interval notation, you're going to use either parentheses or brackets or some combination of the two. Remember, a bracket tells me a value is included, a parenthesis tells me that that value is excluded. So what I'd like you to do is pause the video and go and answer these questions, come back and check your answers. Okay, so these are your answers. So if you've gotten these answers correct, just move on. There's no reason for you to listen to an explanation for material that you obviously understand. If you didn't, then I'll do a brief explanation. So for part A, f of 0 is equal to 0. So I'm looking at, okay, where is the point that if x is equal to 0, what's the y value? And so you can see if x is 0, y is 0, that's the point 0, 0. F of 6 also equal to 0. So when x is equal to 6, so here's where x is equal to 6, I can see I have a value, y value of 0. F of 8, now f of 8 does not exist because that means when x is equal to 8, what's the y value? Well, I can see the graph ends when x is equal to 6. So f of 8, DNE stands for does not exist. 8 is outside the domain. So this is outside the domain, okay, which means there is no y value associated with it. The graph does not exist at that point. For f of -2, I have 1, and so that's the point here. When x is -2, y is equal to 1. Is f of 1 positive or negative? So when x is 1, which would be about right here, I can see that the point on the graph is around here, somewhere around -1, -1.2, and they just want to know is it positive or negative, and obviously the y value would be negative. And then if f of x equals 3, so what I'm asking now is when y is equal to 3, what's the x value associated with it? Well, the easiest way to do that is to find where y is equal to 3, and I usually just kind of draw a dotted line across and figure out where do I intersect the graph. Well, you can see you intersect the graph here, okay, and so the associated x value is 5. For part D, identify the x-intercepts and the y-intercepts. So x-intercepts, remember, are we touch across the x-axis, so I would have 1 here at, let's use a different color. I'd have 1 here at 0, 0. I would have 1 at 4, 0, and then of course another one at 6, 0. Those are my x-intercepts. My y-intercept is where I touch across the y-axis, so that value would be at 0, 0. So again, the 0, 0 are the same points. They're both xy coordinates. X is 0, y is 0. And it happens to be one of them it represents both an x-intercept and a y-intercept. Now for the domain, you should have -4 to 6. Make sure you have brackets because the values are both included. When I'm reading the graph from left to right, my smallest x value is at -4, and then I read across, my largest x value is at 6. That was a closed circle there at 6, 0, so both of those values are included, and so you should have -4 to 6 with brackets. The range, again, for the range, I read from the bottom to the top, so I'm starting with the smallest y value. So the smallest y value I can see is at -2, it's here, and then as I read all the way up, the highest point on the graph is at 3. So for your range, you should have -2 to 3, again with brackets, because there are no open circles. It's closed circles, which means the graph exists at those points. Okay, so hopefully you did well. Okay, so now we're ready to talk about one-to-one functions. So a function is one-to-one when each value of the dependent variable, remember the dependent variable is the range or the y values, that's dependent because it depends on what x is, corresponds to exactly one value of the independent variable. Okay, remember the independent variable is the domain or the x values. Okay, so in other words, if f of x1 is equal to f of x2, so that's two outputs, you could think of that as being maybe y1 is equal to y2, then we know that the inputs x1 and x2 also have to be equal to each other. Because the only way that that's going to happen is if the outputs are the same, the inputs have to be the same if each each value of the dependent variable, so each of the y's, has exactly one x associated with it. So the way to remember this a little bit easier is just to say that every every y value has only one x value. Now remember, when we talked about function up above, we said a function, oh, it's on the previous page. A function is when every x value has only one y value associated with it. So now we're saying every y has only one x value associated with it, okay? So the reflective property of the graph of an inverse function gives us a geometric test for determining whether or not a function has an inverse function. So much easier than trying to go through and look at every y and determine is there only one x associated with each y, okay? And that test is what we call the horizontal line test. Okay, and so what we know is this. When we're talking about one-to-one functions, okay, in order to be one-to-one, you first have to be a function, okay? So a one-to-one, we talk about a one-to-one function. So if you have to be a function first, then that means you have to pass the vertical line test, okay, where every x has only one y associated. In order to be a one-to-one function, so more restrictive, then in addition to passing the vertical line test, you also have to pass the horizontal line test, okay? And just like the vertical line test means it can only cross the graph in one point, otherwise it fails. Horizontal line test means when you draw a line horizontally, it can only cross the graph in one point, otherwise it fails. So it's the same idea if you remember back in geometry class, that it's much easier to be a rectangle than it is to be a square. Okay, every square is first a rectangle and then a square. Okay, every rectangle is not a square. So similar idea. You have to first be a function, pass the vertical line test, and once you pass the vertical line test, then if you also pass the horizontal line test, then you are a one-to-one function, okay? And so you may be wondering, why on earth do I care if something is a one-to-one function? Well, where this plays in later is this, which is really interesting, is one-to-one functions have inverses, okay? And if a function has an inverse, what that means is, let's say I have a function, let's say f of x, and let's say there's some points, we'll just create some points around this graph. Maybe 1, 2 is on the graph. Maybe 3, 4 is on the graph. Maybe 5, 6 are points that are on the graph. Then if it's a one-to-one function, then it has an inverse, and we write the inverse as f inverse of x. Okay, this comes a little bit later in module 1. And what happens is the points on the graph of f actually flip. We interchange the x and y values. And so if the point 1, 2 is on f of x, then 2, 1 is on the inverse. 3, 4 is on f, 4, 3 is on the inverse. 5, 6 would become the point 6, 5. Okay, so we use this one-to-one test or this horizontal line test to determine if a graph is one-to-one. If it's one-to-one, it has an inverse, which comes with all these really cool properties. And so we'll get to that later in module 1. Okay, so again, back to our horizontal line test for inverse functions. So a function has an inverse if and only if no horizontal line intersects the graph of f at more than one point. Okay, and if no horizontal line intersects the graph at more than one point, then we know that no y value is matched with more than one x value. And that's the essential characteristic of what we call one-to-one functions. Now you can write one-to-one, you can write it out as the words. Sometimes you'll see that I shorthand it as 1-to-1. Okay, either one is fine, either notation. It doesn't make any difference on your homework and such that you're going to turn in. I'll take either one. Okay, all right, so let's go through some examples down here and let's determine which of these represent functions that are one-to-one, and then therefore that means they have an inverse. Okay, now remember, to be a one-to-one function, you first have to be a function. Once you're a function, which means you pass the vertical line test, then you have to, in order to be one-to-one, you have to pass the horizontal line test. So what I'd like you to do is pause the video again, go through, determine which of these are one-to-one functions, tell me why. You have to always support your answer. You can't just guess. So like if we were on a test and I asked you if it was a one-to-one function or a quiz or a homework, you can't just tell me yes or no. You have to tell me yes or no, and then you also have to tell me why. How did you know? Okay, so answer each of these and then give me some support for how you knew. Come back and check your answers. Okay, so for the first one, which is labeled number 44, that is a one-to-one function. It passes both the vertical line test, which means it's a function, and the horizontal line test, which means it is one-to-one. And when I say it passes, you can see the vertical line test. If I draw a vertical line, at no point am I intersecting in more than one point. So even when it gets over here to the far left of the graph, it's still bending just enough that with my vertical line, I'm not intersecting in more than one point. And then when I look at my horizontal line test, same thing. I draw a horizontal line and I don't intersect the graph in more than one point. So that's one-to-one. Number 48 is not one-to-one because it's not a function. It fails the vertical line test in a multitude of points. So you can't be one-to-one if you're not a function. You have to first be a function. Then one that's labeled number 63 is one-to-one. It passes both the vertical line test and it passes the horizontal line test. Okay. Number 65 is not one-to-one. Okay. Now it passes the test to be a function. Okay. I can draw my vertical lines and I'm okay, but it fails the horizontal line test because obviously if I draw a line, I'll intersect in multiple points. And all I have to do is fail in one place, and I have failed. Okay. Number 68 is not one-to-one because although it is a function, passes the vertical line test, it is not one-to-one because obviously it fails the horizontal line test. So now what I'd like you to do is I'd like you to draw a graph that fulfills the following characteristics. I need it to be a function, which of course means that it's going to pass the vertical line test, okay? It's not one-to-one, which means it's going to fail the horizontal line test. I need the value f of 1 to equal 3. And then it has a domain of negative infinity to infinity. So pause the video here. See if you can create a graph, and there's a multitude of graphs you can come up with that meet these characteristics. Okay, so I've got 3 different examples here you could have drawn, and like I said, there's 1,000 different things. You just need to make sure that your graph includes the point 1, 3. So I have this one here. If I had drawn this on the grid, it would be at 1, 3, would be at 1, 3. It's not one-to-one, so whatever your graph looks like, it should fail the horizontal line test. So you can see my graph here absolutely fails the horizontal line test, as does this one. Now, the one here is a little harder to see, but because that's the graph of a constant function, if this were to go through, let me add a grid to this just to make it easier to understand what's going on here. So this is 1, 2, this would be 3, okay? You can see if I drew a horizontal line through the graph, well, a horizontal line through the graph would lie exactly on top of the graph, and so it would hit an infinite number of points on the graph. And then, of course, each one of my functions here has a domain of negative infinity to infinity because they continue forever to the negative and this direction, and then continue forever to positive infinity. Now for number 2, we're supposed to draw a graph that fulfills the following characteristics. It is a function, which of course means it's going to pass the vertical line test. It is one-to-one this time, has to pass the horizontal line test. F of -2 is going to equal -1, and it has a domain of -3 to 3. Now remember, parentheses means -3 is not included, and then the bracket means +3 is included. So pause here and see what you can do with this. Okay, so again, there's a multitude of graphs that you could have drawn. Just make sure your graphs have all of the characteristics. It is a function, so it has to pass the vertical line test. You can see mine does. Is one-to-one, so it has to pass the horizontal line test. Again, mine does. Has the point where f of -2 is equal to -1, which means you have the point -2, -1 on your graph. For me, that's right here. And then my domain is from -3 to 3. Now, -3 with the parenthesis means it's not included. That's the reason I use the open circle here, because that point actually doesn't exist on the graph. So from -3 to 3, 3 is included, +3 is included, so I used a closed circle. So your graph should not exist beyond to the left of -3 or to the right of +3. Your graph should only exist between those two values. Okay, so again, you could have a multitude of things. Just make sure that your graph has these characteristics. Okay, so now I'd like for you to open up your lab manual, which you'll find on Blackboard. And we're going to do a little bit of practice. On pages 4 through 7, part 2, I want you to complete the graphs for numbers 1, 3, 5, and 6. And then also identify the X and the Y intercepts. And then on page 6, you're going to complete part 3. So once you've completed all of that, you just need a little more practice just to nail down these concepts. And then the key for Blackboard, you can find in the course resources folder. So in the course resources, which is on Blackboard, okay, you will find the key so that you can check your work. So again, take a break here from the video, go work those handful of problems, check your work with the key, make sure you're on track, and then come back and finish the last page of your notes. Okay, so this is a page that shows some graphs of some basic functions that we're going to be using throughout the semester. So you will see these over and over again in different formats from now until we finish up at the end of the semester. So we need to go ahead and memorize these, memorize them in two different formats. One, we need to memorize that if I give you the graph, you recognize what sort of function it is. If I give you the graph of a root function, say, then you can tell me it's a root function. So I might give you this graph, and then you would tell me it's a root function. And then from there, you could also tell me what the formula is for that particular function. And then the other way that you'll want to memorize them is if I give you a function, so maybe I give you f of x equals the square root of x, then you should be able to visualize in your mind that what the graph looks like and create a sketch of the graph. So it might be helpful to create some flashcards or something, put the graph on one side, the function name and the function on the other side, and just and work on both ways. We need to go ahead and get this nailed down so that as we move forward through the course, you can visualize when I talk about, a cubic function, you can visualize what that looks like. This one's a cubic. And then you automatically know that the function would be f of x equals x cubed. Okay, so let's talk through each one of these. Let me remove all of this. And we'll go through just sort of some basic properties. So first, we're going to start with linear functions at the top. So linear functions are functions that are written in the form f of x equals mx plus b. And so just a quick review from high school, mx plus b. B, of course, is your y-intercept. It's where it intersects the graph on the y-axis, and we get that value because we know the y-intercept occurs when x is equal to 0. So if I put x equal to 0 into this equation, so I put in 0, m times 0 would of course be 0. So that means that f of 0 would equal b. So the point on the graph is 0, b. That's your y-intercept. And then in the graph 2, m is of course equal to the slope. So quick review on slope. Slope is change in y over change in x, so or rise over run. So if I give you a slope, maybe I give you a slope of something like 1/2. Then as you graph this, you would start at the y-intercept or 0b, and then for this one, your rise over run, you'd go up 1, okay, and then you'd go over 2, up 1 over 2, and that's how you'd graph, or you'd go down 1, back 2, because that would be the same as -1 over -2, which of course simplifies to +1/2, and so down 1, back 2 if we were graphing this. One more example, so maybe m equals -3/4, so of course it's a negative slope, so that would mean you would go, when you were graphing from the y-intercept, down 3 and over 4. Okay, so in my particular example over here on the left, you can see I start at whatever the y-intercept here, that's whatever the value of b is, and then for whatever the slope is, whatever m is, you would go up some number of values, and then over that same number of values to get a point on the graph. So up 1 and over. Okay, so quick refresher. So if you need a little more refresher on lines, if you go to WebAssign, there is what's called a just-in-time assignment that reviews lines and slopes and y-intercepts, just to bring all of that information back. It's a prerequisite still for the course, so you need to make sure that you definitely get as much of a refresher as you need there. So, okay, so back to our linear functions. So I have two kinds of linear functions here. The first on the left is actually a constant function, and there is no slope. So for a constant function, whatever value I put in for x, I'm going to get the same value for b. So if I put in 0, I get b. If I put in 1 for x, I still get b. If I get 2 for x, I get whatever b is. So that's a constant function. It just creates a horizontal line, okay? And of course, f of x equals mx plus b is what we think about for a linear function, where again, b is the y-intercept and m is the slope. That in this particular graph, you can see it has a positive slope. If it had a negative slope, I'd be looking at something like this. Okay, now remember, you read a graph from left to right, just like you read a book from left to right. Okay, so next we're going to talk about polynomial functions. So polynomial functions are written in the format of f of x equals x to the n, where n is some degree. And there's lots of different polynomial functions. Polynomial functions are just smooth, continuous curves. So no breaks, no jumps, no holes. Smooth, continuous. I think I'm missing it. Okay, smooth, continuous curves. Example, you could have something like f of x, 2x to the 7th plus 4x cubed plus 17x minus 46, something along those lines. So I've got, this would be a 7th degree polynomial. Now, two polynomials that you're going to see over and over again that we're going to use extensively throughout the course are a quadratic, which is the graph here that's on the left. Okay, a quadratic is degree 2, so f of x equals x squared, and its graph is a parabola. Okay, this should all be familiar. You should have learned this in high school. And then f of x equals x cubed is a cubic. Okay, so a third degree polynomial is a cubic, and this is the graph of a cubic. So again, if I talk about a cubic, you should be able to visualize what the graph looks like. Talk about a quadratic, you should be able to visualize a parabola. Moving on, we've got a root function. So a root function is we'll use the terms interchangeably. Sometimes we call it a root function, sometimes we call it a radical function. They mean the same thing. So the most common, of course, is the square root. So this is the square root. Okay. And this is the graph. And then finally a cubed root. And this is the graph. Okay, and so we can have even degree roots, like a square root, so which is degree, raised to the 1/2 degree, or we can have odd roots, which would be x raised to the 1/3, or the cubed root. So both of those, if we have even or odd, there will be some variation of each of these graphs. Okay, moving on, rational functions. Rational functions are written in the form f of x equals 1 over x to the nth degree. So it could be to the 3rd degree, to the 1st degree, to the 17th degree. Okay, for rational functions, we get sort of this boomerang shape in each of these graphs. The one on the left maybe looks a little bit like a butterfly, sometimes think, but typically rational functions are those that look like boomerangs. Okay, and so the one on the left, f of x equals 1 over x. And then we have the graph on the right where f of x equals 1 over x squared. So 1 over x, of course, x is to the 1st degree. And so that gives us that particular shape for a rational function. For the one on the right, I've got 1 over x squared, so an even degree. And that means both pieces of the boomerangs would be above the x-axis. So now another interesting attribute of rational functions is that they have what are called asymptotes. And we're going to go much deeper into asymptotes a little bit later in the course, but we'll touch on it here. So rational functions have asymptotes. Okay, and so if I'm looking at the graph on the left, I can see this asymptote actually creates what you can sort of think of as like a wall that the graph runs up against but never crosses. And again, here the graph runs right up against that wall or that asymptote, but never crosses. So this one is called a horizontal asymptote. I'm going to abbreviate, and it occurs at y equals 0. Now I also have another asymptote. I have a vertical asymptote here. So if I can draw this line straight. So this is a vertical asymptote. I'll just use VA for that. And that occurs at x equals 0. And again, the graph runs right up along but never touches or crosses the asymptote. Same thing here. Okay, now if we want to look at the asymptotes for the graph to the right, again, I have a horizontal asymptote here. And again, the graph runs right up along, but never touches or crosses the asymptote. And then here's my vertical asymptote, and graph runs right up along, but never touches or crosses. So anytime we talk about a rational function, you can immediately know, okay, I've got asymptotes. And as time goes on and we work more with those, you'll learn to look for those asymptotes and where do they occur. And so we'll talk about that much more later. Okay, so next, let's moving down, exponential functions. So exponential functions, if you remember, you dealt with a lot in high school. So we talked about things like exponential growth and exponential decay. So an exponential function is in the form f of x equals b to the x. So I've got this base that I start with, or some amount that I begin with. And then that amount either grows or it decays. So let's talk about decay first. So that's the graph on the left. So I start with some amount. You know, a lot of times in your textbooks in high school, it was like cesium-242, and you're told it had a half-life of 17 years. And so if you start with a 100-gram sample of whatever this substance is, then in 17 years, I think that's what I said the half-life was, in 17 years, you'll have half as much. So you'd have 50 grams. 17 more years goes by, you have 25 grams. 17 more years goes by, you have 12.5 grams. And so you continue this process until you get very, very close to 0, but you never actually touch 0. And so that gives us exponential decay. So when we talk about exponential decay, that base, b, is a value between 0 and 1. So a fraction or a decimal, and that's what gives us the exponential decay. So we can also have exponential growth. And exponential growth in your textbooks in high school was typically in the amount of bacteria. And so maybe you start with 2 bacteria, and let's say it doubles every day. So if I start with 2 bacteria on Monday, then on Tuesday I have 4 because it doubles. And then if I have 4 on Tuesday, which means on Wednesday it's going to double again, and I have 8. And so on Thursday I'll have 16, and then on Friday I'll have 32. And so that's an example of exponential growth. And so in our function f of x equals b to the x, b will be some value greater than 1. And so that tells me whether it's exponential growth or it's exponential decay based on the b value in my function. So that's exponentials. From there, we can talk about logarithmic functions. So logarithmic functions are actually inverse of exponentials, and we'll talk more about that later. So logarithmic functions are those that are in the form f of x equals log base b of x. And again, I can look at the value for b, and that will tell me whether or not I'm dealing with exponential growth logarithmic growth or logarithmic decay. So if I have logarithmic growth, which is the graph on the left, then that means the value of b is greater than 1. And if I have logarithmic decay, which is the graph on the right, then b is some value less than 1, but greater than 0. So again, a decimal or a fraction will give me logarithmic decay. Now, a couple things to note here for my exponential and logarithmic functions is they also have asymptotes, just like rational functions have asymptotes. So look back over to the left, exponential functions here, and you can see they have an asymptote, a horizontal asymptote here at y equals 0. The graph comes down, gets very, very close to that asymptote, but never touches, never crosses. So we have a horizontal asymptote at y equals 0. So I'm using HA as an abbreviation for horizontal asymptote. Now, look at the logarithmic functions. For logarithmic functions, I actually have a vertical asymptote at x equals 0. Okay, and so you can see again, the graph gets very, very close to that vertical asymptote, never touches, never crosses. Okay, so those are our exponential and logarithmic functions. And then finally, our last graph that we have is an absolute value function. So f of x equals the absolute value of x. This one's relatively easy to remember because the graph looks like a V. So absolute value, which begins with a V, and the graph looks like a V. We only have positive values on the graph. And so those are your graphs that you need to memorize. Again, make sure that you if I give you a function, you can visualize what the graph looks like, or if I give you a graph, then you can tell me the name of the graph. So maybe it's a polynomial, maybe it's a rational function, and then also you can give me the formula for that particular function.